Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's a pleasure to have Yintat Lee from MIT today. So Yintat has been a supplier of fast algorithms in the recent years, and today he will tell us about a new fast algorithm.
I'm pleasure to give a talk today. This is the first time I present this talk. The result is not on archive yet, but hopefully in a month or 2 months. So this is a journal with Aaron and Sam. So our problem, in this talk I will present 2 problems and 2 algorithms with same running time. The first problem is the feasibility problem. So the setting is like this. So you are given a convex set K here. You don't know where is it, but you know it is inside a ball with radius R. And you are given an oracle to see where is the set. You can ask whether a point is in the set K or not. If it is not in K, then the oracle will give you a hyperplane that separates the set K and your point X. Otherwise, for example, this point again, then it will separate again. And then you want to keep asking until the oracle tells you yes. And our goal is to find some point X in K. And certainly, if the set K is super small, then there is low hope to finding it. So we will assume the set K contains a ball with radius epsilon. And our result is like this. So we can solve the feasibility problem in like n oracle call with extra work n cubed with some polyglot term. Just in case people haven't seen this problem before, I will give some example. For example, you can use the feasibility problem to solve a linear program. For example, this one. The thing you need to do is just write down to solve this problem. That means you want to find an x such that the cost is say less than the minimum cost plus epsilon. Then you just write down the convex set K is the intersection of ax greater than b, and then the cost is less than optimal plus epsilon. And then notice to check whether a point is in K is very easy. You just compare ax, b, and c transpose x. And whenever the point is not in K, then that means there is one inequality it violates. Then you just output that inequality. That is a separating hyperplane. And notice, say, assume A is a square matrix. Then implementing this oracle only takes over n square time. And because our algorithm, the time is n call plus n cube extra work, and you substitute the cost of the oracle is n squared there, then you get solving an LP is n cubed. And this algorithm almost didn't use any structure about LP. By the way, the current fastest algorithm for solving LP is n to 2.5. And another problem I will discuss is the intersection problem that is less famous. But I think this is a very important problem. Now we are given 2 convex sets, K1 and K2. Again, we don't know where is the convex set, but we know both convex sets is inside a ball with radius R. This time the oracle is different. This time our oracle is like we input a vector D, and then the oracle will find you x1 in K1, x2 in K2, such that the x1 optimizes the D transpose X in the convex set K1, and x2 optimized for the K2. And our problem is for any vector C, we want to find an X that is inside the intersection of 2 convex sets, and that almost optimizes the vector C. And to be more precise, again, you can never find the intersection if the intersection is just one point. So we are only able to guarantee you your point is close to some point in K1 and some point in K2. And then again, the result is same result. You can solve this problem in n oracle call with n cube extra work. Now we give some example for this.
Wait. So, so x, the only guarantee on x is this. That's that it is close to some point in K1 and some point in K2.
Yeah. And because of this, they also guarantee x1 close to x2. The problem is, I don't say if I assume K1 and K2 have a small ball, my current algorithm cannot find a point inside that. I haven't thought about that too much because for most of my application that is enough. Anyway, again, some example. For example, now we want to solve intersection of three convex sets. Then how can we use the algorithm to solve? The way to solve it is you consider K1 is the product of three convex sets, and then K2 is the diagonal part. Then the intersection is just the intersection of three convex sets. So again, you can use that to solve LP, because LP, for example, this type is the intersection of ax equals to b and x squared and 0. And both problems is easy to solve. And the first problem is just a linear problem. The second problem is some explicit formula. To be more precise, remember, I need to assume the convex set is bounded, so you need to add something large number here to make sure this is bounded, and then do some analysis saying this is okay. But yeah, and in the very end of this presentation, I will give more example why we care about this problem, like submodular minimization. So now I will talk about the previous work about the feasibility problem. So first of all, why this can be solved. Turns out there is a very natural way to solve this. Again, we want to find a point inside that convex set. We don't know where is it. So, and we assume, say, now the convex set is inside some convex region. Then one natural way to do this is you ask the oracle at the center of gravity. Then the oracle, if the center of gravity is not in the convex set, then the oracle will give you some hyperplane separate the set. And because there is center of gravity by some convex geometry, we know the remaining part has the volume at most 1 minus 1 over E of the whole volume. That means each time we are decreasing the volume by some constant. And because we promised the initial convex set is bounded inside a ball with radius out, that means the initial volume is out to the n. And we promised the convex set contains a small ball, say epsilon to the n has the volume. And because each time we decrease the volume by constant, that means it takes like n log r over epsilon to find that set. And turns out this is tight, almost tight. So this algorithm using center of gravity, you can solve this problem in this number of iterations. Notice is log to the base 1 minus 1 over E. And you can prove a lower bound like 1 over 2. The way to prove the lower bound is just each time the oracle always gives you the side with larger volume. So each time you can only decrease the volume by half. So it's just off by 30%. So the main problem for this problem is how can we make each iteration faster? And there is a lot of work trying to solve this problem, and they are all fit inside this framework. Say you imagine initially you have a region omega 0 that contains the solution. For example, you pick a omega 0 containing a radius of R ball, and then the algorithm keep finding a certain center of your convex set, and then ask the oracle if the center is in the set, then you're done. Otherwise the oracle will tell you a certain half space contain that set. So you intersect your current set with that half space, and you use that information to shrink your set omega. And basically, you want to prove a theorem like this. Each time you can decrease the size, maybe it's volume or radius or something else. You want to decrease the size of the convex set by some constant, then we are good. So now talk about the previous work. The most famous one is the ellipsoid method. Each time you maintain an ellipse, and then each time you ask the oracle at the center of the ellipse, and then you measure the size by the volume of the ellipse. And so the algorithm is like this. You have an ellipse, and then the oracle gives you a half space, then you find the smallest ellipse containing the half ellipse. And then you can prove each time it will decrease the volume by 1 minus 1 over n. And each iteration, this algorithm take n squared. You can think n squared is, I don't know, I would think this is the best you can hope for because you need n squared information to store ellipse. And however, this algorithm have a very slow conversion rate, and in practice, it really converges in that rate. So this is not good for practice. And for example, the previous slide, I showed the center of gravity method. Each time you maintain all the information you get, and then you ask the oracle at the center of gravity. This gives you some constant rate improvement. However, each iteration you need n to the 6th time to do this by some sampling technique. And there is many methods to improve about that. For example, there is one by Kachin. This one is, again, you maintain all the information to store the whole polytope, and each time you compute the largest ellipsoid inside the polytope, that is called joint ellipse, and then you ask the oracle at the center of joint ellipse, and then you measure the progress by the volume of joint ellipse, and it guarantees each time the volume of joint ellipse decreases by some factor. And then the cost is much better. The cost is just compute a joint ellipse. And turns out you can do it in n to omega plus half time, plus 1 over 2 times. Omega is the fast matrix multiplication constant. And the previous best result is by Vaidya. That one is using volumetric center. That will be like 30% of this talk, so I will not give you here, but the rate is something like this. Again, it's constant, and the cost per iteration is just inverting a matrix, so it's n to 2.3 something. And you can think this result, we improve that to n squared. And I somehow feel this is the lateral barrier for this problem because you need to maintain some sort of ellipse. Anyway, to motivate the Vaidya paper, you can think all of this result is trying to get a sense of how can we compute a volume faster. For example, you can think ellipsoid method is approximate an object by some random ellipse and then use that volume. And then the center of gravity, you use the real volume, which is super difficult to compute. And then we know the joint ellipse have some rounding property. That is a better approximation of the volume of polytope. And later on, you will see the Vaidya algorithm also give you a pretty good estimation of volume. So to motivate the method, let us focus on symmetric polytope. Imagine you have a symmetric polytope like this one, a is less than 1, and we want to estimate the volume of this one. How can we do this? One of the methods is you replace the L infinity long by L2 long. And by Cauchy-Schwarz, you know that if you decrease the size of the polytope by square m, it will inside the ellipse. So this is square m to the n approximation of. If you use the volume of that ellipse, this is some exponential approximation of the volume of the original polytope. This is good approximation for cutting pin method because remember each time we are decreasing the volume by some constant. If the approximation is just exponential, that means we just need to take extra n iteration to recover this approximation. So this is good for us. So we have an easy way to estimate the volume for symmetric body. How about a symmetric body? Like this one. In the previous slide, for example, the way to do this is you take any point inside the convex set, then you flip the convex set x minus k, and then you take the intersection. Notice the intersection is a symmetric body. Then in the previous slides, we give an approximation for symmetric body, that ellipse. So and notice this is the lower bound for the volume of k. So what is the natural way to estimate the volume of k? Is you find the best point, maximize the volume of that ellipse, and we define that is the size of the k. And for polytope, you will have some nice formula to write down what is the size of k. Turns out it is more convenient to consider log of 1 over size of the k. You just do some algebra because volume of ellipse is just determinant of something. So turns out this log of 1 over size is just the minimum point of the log determinant of A transpose S inverse A. S is the slack of a certain point. Slack is the distance to the constraint. And you can prove a theorem like this. This is still a good approximation. This is still some exponential approximation, m to negative n. So which is good for us. We just pay n more iteration or n not m iteration, which is good. And from now on, I will focus on the notation f because it is more convenient. Because the f will take the log. So you can think our goal is to increase the f by O tilde n. And remember, our goal is to shrink the volume by some exponential n. That means we want to, and our goal is only pay n iteration. That means we want to increase f by some constant each iteration. And now we have the proposed algorithm for Vaidya. I mean the Vaidya proposed algorithm. You start with the convex set is a box because you want to maintain it as a polytope. You don't want the ball. The algorithm each time. Okay, yeah, remember we already introduced the notation for the approximate volume. Then what is the point we should pick? Then the natural point is the point where we use the x because that is the center of that ellipse. Then each time you.
So if k was a Euclidean ball, what would be f of k in this case?
That will be exactly log of 1 over volume of that ball. Yeah.
So in that case, it would be exact.
Yeah. Yeah, so each time you look at the center of that ellipse, and then the algorithm is just like this. You ask the oracle, and then if it is there, okay. Otherwise, you maintain all the information. You intersect the half space with your current polytope. And now we want to prove each iteration the f increased by constant. And turns out people believe that, but nobody is able to prove that. But before talking about that, we try to see why it's bad.
And how do you compute CK?
CK, I will talk about that later. Yeah, you can use Newton method. Yeah. So there is two effects affecting the function f. For example, the current polytope is this one, and then the oracle will give you this hyperplane. And turns out for some analysis purpose, putting the hyperplane exactly at that place is difficult for analyze. You want to put it slightly off, then Taylor expansion, you can use Taylor expansion. Anyway, so after you put the hyperplane in there, then the next iteration, the polytope is look like this one. And you notice there is two things change for the ellipse. First is the center change, and also the shape of the ellipse change. So we want to understand which effect is more important. And to see this, I define G is the log that A transpose S inverse to A. And then you just take Taylor expansion. You want to compare the real polytope K prime, f of K prime minus Fk. because there is two effects, so you have the grad A and grad X. And notice X is the minimizer of the function G, so this term disappears. That means you only have one term. So in some sense, it says the change of X only gives you some second order term for the F. So from now on, I will assume there is no X. You only try to understand when you change A, how much the F will change. And turns out this is super easy to do. Because we assume X doesn't change, so you can also assume the sled doesn't change because sled depends on X. So you can just think the F is log that of A transpose A. And when you have a new constraint like this one there, then your new polytope is like you add a new row in the matrix A. So the size is just log that of A transpose A plus a rank matrix. And we know there is an explicit formula for what is the volume. You can relate them. Turns out it's just changed by log that A plus this 1 plus this term. And notice A transpose, this term is positive. That means the whole term is positive. So if you ignore the second order term, at least this tell you the F is increasing. However, and also, if you know about left phase score, this is left phase score or effective resistance or blah, 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 blah.
I'm just confused. Why don't you want F to decrease? F is supposed to be the size of the thing.
It's 1 over, yeah. And anyway, for us, it's better to look at the picture. Yeah, again, assume the polytope is symmetric, easier to draw, and then this is the ellipse. And then say you add the constraint there. Turns out the A transpose some inverse A is this one. The one here is because we assume the distance is 1. And then turns out this term is just the distance here. And you can imagine generally they are always constant if the polytope is not too crazy. However, if it looks like this, then it's bad. So if you put the constraint there, then again remember the definition of A transpose A is here is 1, and then the A transpose inverse A is here. This term here, you can see from the picture that term is 1 over M, so that is bad. Certainly, you can put the constraint closer because your constraint originally is exactly cutting at the center. And turns out for some reason you cannot do that because there is a second order term. The reason is, remember our center is here. And then if you put the constraint that close, then that constraint is trying to push away that center. Then that center go too far away. And that is bad. Yeah, so now we discussed the amazing idea for Vaidya. The idea is quite simple. When we put the constraint there, the F will increase by that term, A transpose some inverse A. When you remove that constraint, then the opposite happens. The F will decrease by that term. So the Vaidya idea is just like this. Again, you start with a box. You repeat. Maybe I should define this. I define this is the importance of a certain constraint. For the constraint A, that I call that is the importance of A. Whenever your polytope there is a constraint that is not important, that means say the importance is less than 0.001, then you drop that constraint, and because of that observation, the F will decrease by 0.01. Otherwise, you ask the oracle and then add the new constraint, and turns out because there is no unimportant constraint, the previous picture doesn't happen, and you can always put the constraint quite close, and then you can always increase the F by some constant larger than that one. And so that implies the F is increasing by constant in amortized. That means this algorithm takes O tilde n step to get the solution. Is there any problem? Any problem?
So when you say if there is an unimportant constraint, you check all of them, or what? Yeah, that's what you do.
Yeah.
Okay.
Yeah, and in the next slide, I will talk about how to check that. Yeah, so the main problem for the Vaidya paper is each step is still expensive, although it is quite cheap. So you can think our algorithm is try to simulate the volumetric cutting pin method by using some randomness technique. So the main difficulty for the volumetric center is to compute the volumetric center. To see why this is difficult, you can look at the automatic condition for this one. Because to get the solution, at least you should be able to check whether the optimal point is optimal. And the automatic condition is look like this. Here, notice the sigma. Here is the importance of certain constraint. Notice the definition is slightly different because in previous slide I assume S is identity. But if you have the S, then the formula is that one. Remember, S depends on your current point X because S is lag. And you can think this constraint is saying this condition is like you have a polytope, and then you have a bunch of vector A. Then it is saying certain convex combination of A will cancel out. And you will rate those constraints by the importance of a constraint. And just to show some picture, for example, your polytope is this one and your point is that, then the sigma are 0.9 and blah, blah, blah. And that is 0.9 because that point is closer to that constraint. Another example, for example, if you repeat a certain constraint twice, then the importance will decrease by half. And another fact is if you sum up all the importance of the constraint of the polytope, then you will get the dimension. For example, this is a two-dimensional polytope. You sum up them is 2. And to compute the center, the necessary condition is we need to compute the left face scores.
So before you're going to remove the unimportant constraint.
Yeah.
But in this case, where there is one which is repeated, you won't remove it.
Oh, this one we still will, because one thread is still large. Turns out in the proof the threshold we remove here is super small.
If there is one which is repeated many times.
Yeah, then you will remove until there is not too many. Yeah.
Because the importance is shared among them.
Yeah.
I see.
Yeah, so again, there is the importance, and the problem is to compute that exactly. One thing again, because this is the automatic condition, so this is the gradient of this function. For example, if you need to do Newton method, then you need to compute that one. And yep.
So is it easy to see? If I remove a constraint, the importance score of everybody will increase?
Yeah. Because your A transpose A is smaller when you remove something, so the inverse is larger. And the another thing is you can think the important is the diagonal part of some projection matrix. You notice that matrix is a projection matrix, and that one is difficult to compute exactly because either you need to compute this matrix exactly, you need to inverse a matrix. For example, if your matrix is sparse, then the inverse of a matrix is dense, so you don't want to do that, at least in practice. Or you can compute that one by one, you solve n linear system, which is even worse. But this is easy to approximate. Because P is a projection matrix, so sigma I is just the norm of PEI. And you can just pick some vector Q coordinate-wise is a normal distribution, and then it's easy to prove. You can estimate the PEI by testing it with random vector, and turns out if you pick something like polylog many random vector, you can estimate all sigma I within some multiplicative constant. So which is good. That means we only need to solve like polylog many linear system to approximate the sigma I. But there is one problem. The approximate center is really bad. Again, this is the original definition of center. And suppose someone already give you a center, and then you try to use the previous slide, those dimension reduction technique to approximate the sigma I. We call it Wi, and you try to compute what is this one. You replace the sigma I by approximate sigma I, and then, for example, for hypercube, then after you approximate that, you in general give you the center is half, and then the approximate center will be half plus or minus epsilon. This is super bad because, for example, the hyperplane is this one. We know most of the volume is inside this band with a distance 1 because of concentration, and here the distance is square n. So you are only cutting some exponential small region. So this is difficult. Turns out our idea is very, we spent a lot of time on this problem, and turns out the solution is very simple. The solution is, instead of using dimension reduction to estimate the leverage score, you estimate the change of the leverage scores. What I mean is, you want to find an estimated W such that there is an estimated, say S is the next step, T is the previous step, and then you want to compute the change of leverage scores. If you can compute that exactly, then you can just add that back and then implement the Newton method. And turns out you can do something like this. You can find an estimator such that there is unbiased with the variance is more in L2 norm. The main reason is, for Newton method, you can think each step is moving in constant distance in some L2 norm. And here, our performance of our estimator depends on how much the step change. And because we're using Newton method, the step is small, so our accuracy is super good. Remember the previous slide, the error is constant in subnorm, so it is square n in the 2 norm. And now we are getting something like constant in L2 norm. And the idea is pretty simple. You just write down the definition of the sigma I. You write down into different parts, and then you notice this term, the W minus V is small, and then this term by previous slide, we know how to estimate that. And because this term is small, so when they multiply, the error is small. Because this is more in L2 norm, so you multiply them, is more in L2 norm.
Can you go back one slide? I'm going to see if I follow what.
Yeah.
So I mean, so what you say is, instead of trying to compute some like the sigma, the leverage scores approximately, and then using this for a center, you just want to find you just want to basically have some. You want to have a direction which points you towards the center.
Yeah.
You want to get closer to the center, and I guess the point is that if you just try to estimate this sum of sigma I AI over SI with like random projections, then this you can do much more accurately than by estimating all of the sigma I's and then using a worst case estimate.
Yeah, something like that. Okay. Okay. I'm sorry. Let me raise the here. The computer is slow. Yeah, so also for this term, notice this is not PSD matrix, so you cannot directly apply dimension reduction, but you can tailor expand this term, and then you have a bunch of terms. Then you can separate those terms such that each term is PSD, then you estimate each term. Those are easy thing to do. So you can think this is the Vaidya algorithm, and then the Vaidya algorithm need to compute leverage score. We just give good management on the leverage score, I mean the importance. So we store the previous sigma I, and then we update appropriately. And in the previous Vaidya paper, he measured the progress by the log depth. And turns out you can think our algorithm is essentially minimizing this function. The D is the difference between the true sigma I and our estimator. Because when you take the gradient, this will give you the extra term. So in fact, we are minimizing that function. And there is one slight problem here is when the DI is very large, then this problem is not convex and bad thing happens. So the simple trick is each time you try to estimate which coordinate has large error, and then you pick the largest error term, and then you recompute that sigma I exactly. And when you compute one sigma I, you can compute it by solving one linear system, so it is not costly. And because our estimator is unbiased, so you have estimation of the little difference is equal to the previous one. Also, because the variance is small, you can think each step the D only changes by constant by L2 log. And the crucial fact we are using in the proof is like, notice if you only measure the L1 norm of D, when you take one step, because the L2 norm change is small, the L1 norm change can be very, very huge. And our proof essentially using the point the estimator is unbiased, so it's like so because they are unbiased, so it's like when you add a bunch of noise to a vector, even you take t iteration, the noise only grow like square root t, and somehow that is enough for our analysis. And now I will switch. And then the next problem is now we have a good estimator of sigma I by solving some linear system. But remember, each iteration we only have n squared cost to solve a linear system. So the next problem is how can we solve linear system in n squared? Certainly we are not directly solving that problem. We are using the fact everything doesn't change too much each iteration. So when you look at the algorithm, you can think we have a matrix A and some diagonal matrix. The diagonal matrix is the 1 over Z square. And then you can think, okay, now we formulate it as a self-alone problem. We call it inverse maintenance problem. The problem is you have a matrix A and a bunch of diagonal matrix, and also you have a bunch of vector. And then you promise each time each diagonal matrix either change by some one coordinate because you add a constraint or remove a constraint, or they change by small L2 log when you take the log. This is because Newton method guarantee. This is because the log that, because our potential function will guarantee that. And also because of our problem, each time you don't have the whole matrix A, whenever a certain entries of the diagonal is non-zero, then the row A will reveal to you.
So do you mean log that, or you mean what do you mean when you?
I mean D is diagonal matrix. You take log of each entry and then compute the difference. Yeah. And our goal is compute the inverse of the B vector in n squared time. For now, say I assume M is roughly ON because we only take ON iteration.
But it could be, but you could start with M much larger than M.
Because we start with a box. with a hypercube.
Oh, you start with blocks. Okay.
Yeah.
Yes.
Yeah. And this result is useful and well studied. For example, this is study for how to solve linear program, because in the interval method, each iteration is solving a bunch of linear system like that. There is many previous results on this. You can see here is the number of constraints. Here is the number of non-zero for the matrix. And you see there is many regions with many different algorithms. They are competing each other. And this result will give you this result square. And basically, you can think if you have an LP with a lot of constraints but not too many variables, then this is just writing the matrix square n time. N is the number of variables. And yeah. Anyway, yeah, so now we see how to do that. Because I want to make the algorithm into one slide, so I only get 2.05. And the first observation is, notice here, say originally you are given D0, and then say after some iteration you have some dr. And just to remind you, the time to compute a matrix inverse is the running time is something like this. So for every n to 0.37 iteration, you can compute some matrix inverse. So you can think now we separate the task into group. Each group have n to 0.37 iteration. And turns out you can prove a statement like this. Each iteration, you can write down the D to R is like some matrix R plus a small error term. You try to group all the change of the coordinate because there is two types of change. Either there is one coordinate change or the L2 lump change. When the L2 lump change, then either many coordinate change together, but when that happens, then those coordinate change are very, very tiny. When that happens, in fact, there is a good case. You can do nothing and then use the D0 to precondition the new system. So you can think we write down all the small changes in the matrix E, and then you can do some analysis and promise that two matrix only change. Here is 0 lump. I count how many will change. Turns out that is just n to let me count 7, 6 or 7, 4. 7, 4 is 3, 7 times 2. Now from now on we can ignore the E part, because for the part E we can use preconditioning to ignore that. So we only have a few will change. And the major trick we are using first is whenever you have a matrix and there is a certain row change and you want to compute the inverse, turns out there is a formula to compute it for you. Yeah, and then you notice, for example, if you apply a B here, then you just apply B here and B here. And because in the initial iteration, you compute the matrix inverse exactly. So you already have the M inverse. So this is easy to calculate. Now with this term from here to there, this term we can compare, and then this term we can compare. Then the only problem is this term, how can we compute that? Turns out, and because we only have my notation conflict with each other. Okay, so here is you take square root R iteration. Now R is 0.74. So after square root R iteration, the M will only change by M R. And then you can notice U is an M by R matrix, and this matrix is an R by R. R by R matrix. Turns out you can compute that. Whenever R is whenever R is more than 0.87, and here is 7, 4, so it's good. But then the next problem is how can you compute the inside matrix? And then notice this is difficult because this is an n by n matrix and this is n by r matrix. And whenever r is super constant, then your running time will be super quadratic. So our next trick is this one. This is a recent result called Olive's embedding. So for any tall matrix, any n by r matrix, there exists a distribution of sparse matrix which does not depend on n, and such also those matrices r by r, such that you have this inequality. You can multiply the n by pi, and then the square is still similar. So using this fact, we can apply it for our problem. And then now the key fact is, remember pi does not depend on n, they are just some random matrix. It is Olive's to n, so we can pre-compute the pi m inverse, negative inverse. And that is an r by n matrix. So you have this, and then so each iteration you just need to compute this with that one. So you're computing an r by n matrix times n by r matrix, and then that is better than n by n times n by r. And that one you can compute in this running time, and then you substitute y is 4 or 6 something. Then turns out you will get 2.05. This is slightly worse than 2, and then turns out there is more trick you can play and then get it down to 2. And this is funny. And this one is easy to summarize. You can think the whole algorithm is you have a bunch of ax equals to b. First of all, you use preconditioning to remove the error part. So each time the previous matrix is just a low rank update of the next matrix. And then you can use that formula for the matrix inverse that is called Wolf-Berry matrix identity. Then you convert the problem to computing a small matrix r by r matrix. Turns out that r by r matrix is a projection matrix. Anyway, and then we use Olive's subspace embedding to reduce that to a truly small size problem, and then use fast matrix multiplication to get an n square running time. Turns out you cannot directly output the solution of this algorithm to your iterative method. The reason is because there is randomness here. And whenever you output the solution, you reveal some randomness to the iterative method. And it's difficult to prove independence or blah, blah, blah like this. Because remember, for many iterations, we fix an n and then use that embedding for many matrices. And if you reveal the randomness to the iterative method, maybe he is an adversary want to kill you, then it's bad. But turns out you can add some noise into the solution, and then you can handle that independent problem. Now we have the algorithm for solving linear system, such a linear system in n squared. Now we can summarize for the feasibility problem. If you don't think the Vaidya algorithm is lateral, maybe you can look at this formulation. Turns out you can prove the ellipse the Vaidya algorithm give you is an approximate joint ellipsoid. That means if you enlarge the ellipse by n, it will cover the whole polytope. So you can think the algorithm is just like this. Each time you find an approximate joint ellipse, ask the oracle, find a hyperplane, and then repeat. The only difference is we have a lot of randomness to speed up. And the funny thing is, it is super close to the fastest algorithm for linear programming. The current fastest algorithm is like this. Each time you move the cost constraint, and then you find the joint ellipsoid for that region, and then and then you try to maintain the center of that joint ellipse and keep pushing the cost and keep maintaining joint ellipse. So it's almost the same. Yeah, and now we can go on to the intersection problem, which is much easier, so it doesn't take a long time. Just to remind you what is the intersection problem, we want to optimize a linear vector on an intersection. And then a famous result by GLS is showing this problem can be solved in polynomial time. And this is the first polynomial time algorithm for many problems. And their proof is based on equivalence between separation and optimization. And our proof, I think, is easier. It is based on a formula. So let me explain this formula. This is the problem we want to solve. And we don't know how to handle the intersection. So we introduce two variables, x and y. They are in separate convex sets. And then you try to penalize. You don't want them to far away. This time I will explain later. Also, you take the lambda super large. And the next observation is you have this formula for the to the square. You can take the deal of the square is still the square. And then using this formula, you can rewrite this problem into this. You replace the square here you can see this term, and this term is replacing x minus y squared into this term, and this term. You can think it's just taking the Lagrangian deal of that problem, and then you swap the min-max. And now notice, now we want to solve this problem. Say I call that function is f theta 1, theta 2, theta 3. And then notice the subgradient of this function is exactly x and y and some formula relate to theta 1, theta 2, and theta 3. So you can compute the subgradient of f by using the oracle. So the key observation is here. When you look at the automatic condition for this settled point problem, turns out theta 1 is equals to x minus y, theta 2 is equals to x, and theta 3 equals to y. That means if you find the minimizer of the function f, then you can just output theta 2 and theta 3, they are x and y. So this allows you to get the deal without any equivalence. Or maybe this is the equivalence. And that is the reason why solving this problem is as easy as the feasibility problem, because you just apply the cutting pin method for that function.
Lambda should come in the picture somewhere.
Oh, lambda. Why lambda is not there? Because here, for this problem, the automatic condition is theta equals to x. So because the theta 1 is the deal of x minus y, so you get theta 1 equals to x minus y. Yeah.
I guess lambda appears if you want the first line to be true, you need lambda very large, but it doesn't appear afterwards.
Yeah. So here in this thing, you have used somewhere that lambda is very large.
Yeah, the lambda will depend on epsilon. Otherwise, your error will depend on some lambda, 1 over lambda.
But there is no error terms over here. Like here, you're writing the optimality conditions.
There is no error term.
I mean for this problem. I mean for the optimal solution for this, not the optimal solution for that. Yeah, so why intersection problem is useful is because many problems you can just write down the linear program and then you can separate the problem into two parts, and then each part turns out it's easy to solve. For example, like submodular minimization, you can separate that into two parts, and then this one you can solve by greedy method. And in fact, there is many problems you can do like this. And the interesting thing is, turns out this gives the fastest algorithm for a lot of problems. For example, for submodular minimization, you just write down the LP and see this is the intersection. Then you get n squared oracle call plus n cube running time. The previous is n fourth oracle call. And for example, for mean cut problem, you have like n squared information because you have a dense graph. Then maybe n squared is necessary or not, I don't know. But for many problems, you can directly apply the intersection problem and get faster running time like submodular flow from n to 6 to n squared and Matroid intersection. Many people don't know about numerical method because it doesn't give you Johnny polynomial time or I don't know. But anyway, turns out this algorithm, if you do some smart thing, you can get a Johnny polynomial algorithm for submodular minimization. To get the taste for this, you can imagine this algorithm. You keep doing the cutting pin method until the volume is super small. When the volume is super small, because the feasible region will contain all integer points. And when the volume is super small, that means those integer points lie on the same hyperplane. So for every n iteration, you decrease the volume by 1 over n factorial, then you can prove there is only one hyperplane. Then you can reduce the dimension and repeat. There is a Johnny polynomial time algorithm. However, I don't know how to detect a subspace, so it's more complicated than that. You need to use some structure about submodular minimization. But yeah. But anyway, also I somehow feel this is a practical method. Although many people think cutting pin method is not efficient because ellipsoid method is slow. I would argue in this way. First, it is parallelizable. Also, this, at least for my cutting pin method, is purely linear algebraic. So our current computer system is very suitable for computing A inverse or solving a linear system. I guess more importantly, recently, Sebastian Mohit and me have a result about ellipsoid method. We get the variant of ellipsoid method. Instead of doing ellipsoid, which is difficult to maintain, if you have large data, you do a ball method. And then you combine it with gradient descent. And turns out it is very efficient. We tested on the worst function proposed by the Lestrov, and the green one is the ball method or ellipsoid method, and the red one is the Lestrov, the popular one, and this one is the algorithm people really use in practice. They store many iterations instead of just the previous iteration. They, for example, store the previous 100 iteration gradient information. You can see our algorithm is quite competitive. At least it shows ellipsoid method can be practical. I don't know if it is competitive, but at least it is not that bad. And I don't know for this cutting pin method, but at least I think it's something. Now I have an exercise. Now consider this problem. Again, we have a convex set. The oracle is slightly different. You have an oracle to minimize linear function plus epsilon. This is still an easy problem. For example, say if the convex set is like this is still easy to solve because you have explicit formula. And this is not like an LP because for LP you have some matrix A inside make everything difficult. And for this one, it is usually easy to solve. And now suppose we want to solve a problem like this. We want to minimize function in the convex set case subject to some linear constraint and assume the number of rows is not too many. Then the question is how fast you can solve this. Yeah, anyway, this is probably a problem you can assign to people. I will just give you a solution. The solution is like this. The main problem you want to avoid is using the variable x because x has n variables. So what you do is you take the dual of the ax plus b, then you have the Lagrangian multiplier here. Notice here the theta variable have only r variables because for each constraint you have one variables. Then you take the dual, then you solve the theta problem, and this is our function f theta. And because our optimization oracle, you can compute subgradient of this. So the running time is RO plus R cube. And notice it doesn't depend on n except the oracle little with the matrix. So why we talk about this is because previously, for example, this LP, for this LP, we know how to solve it in square R iteration using integral form method, and that paper is super complicated. And also that is very specific for this convex set. It's not a general convex set K, but this one gives the fastest mass flow algorithm, and this one didn't use anything and still achieve a number of iterations does not depend on n. This is just by hiding the number of variables by putting that somewhere. Honestly, I don't totally understand what is this going on. For example, in the previous slides, I have the submodular flow problem. I need to use this trick to hide some y variables to get the fastest running time, and that is funny because I don't know what is really going on, but anyway, this is a useful trick to speed up an algorithm without knowing what's happening. Yeah, so this is the summary. Yeah, thank you. And at the end, I have this open problem. How long does it take to solve a submodular minimization problem? Can you do better than n cube time or n square oracle call? Because I somehow feel because the graph have n square edge, maybe you can put a lower bound like n square, then you get a tight result for submodular minimization. Yeah, thank you.
So can you go back to the list you had for the oracle calls? Yeah, this one. So here you're again finding approximate ones, right? Are these approximate?
Approximate? That two is weakly polynomial. First two is weak. This one is weakly polynomial. Everything is weakly polynomial except the last one. This one is Shawnee, and they are weakly polynomial.
No, but is the solution like are you giving integer solutions?
Yeah.
So you do round it as well.
Yeah.
At the end.
Yeah.
This one, okay.
Yeah.
Also for the lower bound you mentioned actually, so it's so these are all like okay. So forget about the running time. If you just look at the oracle calls.
Yeah.
So there nothing is known actually. I think the only result almost nothing is known. There was a result by Harvey, Nick Harvey, who basically proved it from n you get trivially to I think 3/2 n by doing a lot of work. So basically it's not n square, although that's what one would say. It should be.
A funny look. I see there is a paper trying to conjecture the Matroid Intersection. The oracle call lower bound. They believe the correct number of iterations is n to 2.5 by some reason. Yeah.
So in the first part, you are relating things to fast matrix multiplication.
Yeah.
If you don't use fast matrix multiplication in that first part,
yeah.
How does this compare with not using fast matrix multiplication?
Okay, then the running time will Yes, very complicated question. I will at least use n to 3.5. That I'm sure it can be done, but I believe it is 3 point something, some number close to 3.
Even without, yeah.
Yeah.
And that, but it's still, if you plug ordinary into all the other ones as well. You're still getting the 0.5 improvement.
Yeah.
On this point here, like even like I thought Groschel, Lubasher, Schreiber also gave a strongly prolonged time algorithm as well, right?
Yeah.
Basically, using again the similar duality,
Yeah.
as well. It's not the latter one were combinatorial. That was really what they were.
All right, let's thank that again.